We're going to talk a bit about OSPF and link state routing protocols now. So instead of just doing a video on only link state routing protocols, if I tried to do that, I'd end up speaking 90% about OSPF anyway. So this is both in one. OSPF is a great example of a link state routing protocol. It's pretty much your primary one when you're talking about those. So we'll go through some of the details of OSPF and some of the generalities of link state routing protocols as well. So link state routing protocols, they use the shortest path first algorithm, the SPF algorithm. That's what's used to check the topology table and determine what the most proper paths are to get to a network. They're much more complex than a distance vector protocol, which simply counts how many hops away a network is. This instead collects all sort of link information and builds a crazy topology table and makes some complicated decisions on that. There's a lot involved, but they're very feature rich. The way they work is it's based off a calculation of the cost of a link, and it does that based on a number of variables to determine the best path. So it uses variables to calculate link cost. And those can be, we'll get into them, but they can be different variables such as bandwidth usage and latency and things like that. It's an open standard for OSPF, but from IETF. So our good buddies, the IETF, helped create OSPF back in the 1980s. So that's been around quite a bit. A lot of these dynamic routing protocols got their start in the 80s or early 90s, something like that. OSPF v2 is what we use in IPv4, and OSPF v3 is used for IPv6. So we're going to be using primarily OSPF v2 here with some examples, but there is a OSPF v3 for those who use IPv6. OSPF is a classless protocol, so we don't have to worry about that whole classful version 2 thing we had to do with RIP. It's very efficient. It's very fast. It's very scalable. Supports security like authentication. It's got a lot of nice features. It has a couple different databases that it uses. There's an adjacency database. There's a link state database, and there's a forwarding database. And the adjacency database is your neighbors. The neighbors are like what I mentioned with egrep. It'll send some traffic to them, say hello to them, and then say, okay, let's start sharing link information. It'll create that connection to the neighbor and keep it up so that it'll store all those neighbors in the adjacency database. There's a link state database, so that's your topology table. This is the fancy part in OSPF, is it gets all that link information and it builds this whole topology table of the entire network, and that's this link state database. We then have a forwarding database. The SPF algorithm will run against the link state database, make its decisions based on what it sees in there, and then it will populate the forwarding database with options, and it'll use those to then populate the routing table. There's also a number of packets that it uses. So it has different messages that it sends. There's a hello, which is used for that neighbor adjacency. It'll send it every 10 seconds and say, hello, how are you? Are you up? Hey, how are you? Are you up? It'll do that every 10 seconds on most networks, 30 on Frame Relay. And it'll send those hello packets on 224.0.0.5, or it will send it on the IPv6 address FF02::5. So basically the same thing. And so that's what it uses to communicate on. Just like we were talking with RIP v2, where it communicates on that one multicast address. There's also a dead timer built into this. So if a neighbor doesn't respond in this period of time, it will remove them from the adjacency table, so it doesn't try to keep sending traffic to them and not be efficient in its communications. There's also a database description. Database description packet. It's a short list of the link state database entries used for checking against the local database. So sometimes they can compare their link states topologies if they want to check things and make sure everything's okay. That's your LS link state database check, more or less. You have a link state request. Which is exactly what it sounds like. It requests more information on an entry. So if it receives a basic information about a link state, you could send back a request saying, hey, can you give me details about this? We also have a link state update. And a link state update is a reply to a request, saying, or it's to announce new information. So these are actually the main updates that are sent out, the main packets. So if you turn on an interface or you lose an interface for some reason, something changes, the link state update is the one that does that. So that's really the big kahuna for packets. And it'll do that for any new information. It'll do it for requested information, something changed. It'll quickly send out a link state update. And then lastly, we have a link state acknowledgement, which is, as you'd expect, it acknowledges a link state update. So it says, yep, I got it, thanks. The way OSPF works and link state routing protocols in general, it'll first boot up, and when it boots up, it'll learn about its directly connected networks. So we've seen that before. So any directly connected, it will learn about first. So if they're configured and they're told to be no shut, then they'll immediately come up in its routing table, and those are ready to go. After that, it will exchange hello packets. It'll send hello packets to its neighbors and try to create an adjacency. It will then build link state packets with information on each link. So it'll create it'll take these directly connected networks and build link state packets for them. It'll then flood the LSP to those neighbors. The routers then collect those LSPs, those neighbor routers, and construct topology map. And then obviously this one would collect its LSPs from its neighbors as well. So everyone then collects LSPs and builds their topology map. Finally, they'll run their SPF. It runs the SPF algorithm and creates its tree, which is then used to populate the routing table. And it'll finally populate a routing table. There's another thing in OSPF which is kind of interesting for large networks, and that's why I mentioned it was scalable before, is you can configure multiple areas. And you'd say, well, what is an area? An area is kind of like the idea of the autonomous systems I briefly mentioned for BGP, where it's a group of routers. And so the group of routers, if you have a whole bunch of routers here, that's right, I'm still going. We have a whole bunch of routers out there, and one link changes. So this link up here goes down. Oh no. I'm going to send out a link state update to everybody. I'm going to send it to my neighbors, which might be these three, and then he's going to send it to his neighbors, and so on. We're going to let everyone know that, oh my gosh, this network went down. Be very scared. Quickly update everyone. Make sure it's not in your route tables. We don't want anything bad to happen. Quick. And then all this flooding is happening. We've got all this traffic going on because we need to quickly get this link state update to everyone's topologies. And then after this happens, there we go, I drew all sorts of crazy arrows. After all this happens, all these updates happen, then we need to quick rerun our SPF algorithm, most likely. So SPF has to do its thing to make sure that there's nothing else we have to accommodate for in our topology, and we can put a new route in if necessary, or make sure that route just stays out. It's going to quick check things and make sure everything's okay. So we don't want that to happen constantly all the time if it's a huge network. So what you can do is basically split them into groups. And you can say, this side is area 1, and then this is area 2. And when you put them in areas, then only these will communicate to each other, and only these will communicate to each other. And then what you'll do is you could have a router in the middle, or routers in the middle, that act as gatekeepers between the two areas, and they could share routes back and forth and make sure connectivity works between those two areas. But it's a way of mitigating excessive traffic and processing needs. So we have multiple areas. But for a small network, you don't have to do that, and it's very common to simply have one area if you have a relatively moderate number of routers. So multiple areas if needed. And we will get into that. There's a number of states that they can be put into. I won't go into those, but there's a feature known as designated and backup designated routers. So there's DRs and BDRs. And when you're on a network that is multi-access, so if you're on Ethernet, for example, if you have Ethernet links between these, it doesn't know if there's other devices in here and there's other routers and things like that. So what it'll do is it'll elect a designated router and a backup designated router, so that it does not flood all those other devices that might be on the network. So the idea is everyone sends their updates to the DR, and then the DR will let everyone know about what new changes might have occurred. That way we don't have this crazy mesh of updates being sent. It'll just centralize that and then give one master king update to everyone else. So that's the idea behind the designated and backup designated routers. Kind of like with Spanning Tree having its own hierarchical system like this as well, with the root bridge and such. So that election for DRs and BDRs only happens on boot, the initial boot of the network. So once it happens, that's it. It'll get locked in place. So if you bring on another router, you don't have to worry about it taking over as designated router and messing something up. That's a one-time deal unless you completely reboot your entire network. Whoever is the highest interface priority gets to win and become the designated router, and that ID looks like an IPv4 address, but it doesn't have to be an IPv4. It's just a dotted notation that looks identical to an IPv4 address. So you can define your own, and the highest wins. So you can configure your own ID priority, or just whatever the highest IP address is, that will win on the system. So from here we'll go into configuration, and I'll mention the router IDs a little bit more since we're going to configure them, so don't worry too much about that. We'll do a little more detail in the next video. We'll go into single area config next, and after that we'll probably break into some access control lists and such.